Thank you very much for the invitation. I'm honored to participate in the 16th conference on Web and Internet Economics. This is a joint paper with Ran Sporodinsky from the Technion. Experts provide us with daily forecasts on various unknown events, such as the weather, economics parameters, prices, and so on. For example, two financial consultants, conditional on some stock price past observations, repeatedly give advice in terms of probabilistic forecast. In the long run, can we tell which expert is better? If so, what is the mechanism for determining this? In our example, is it possible to determine, after the fact, which consultant predicts the realized stock price sequence with higher accuracy? More general, can two forecasts be compared? So at the beginning of each period, denoted by T, an outcome, omega sub T, is realized from some finite set. For simplicity, we consider just two elements, 0 and 1. But just before the outcome at period T is realized, two self-proclaimed experts, sometimes they are referred to as forecasters, simultaneously announce the forecast in the form of a probability distribution over the set of all outcomes. So our experts should determine their forecast. We assume that experts uses a mechanism in order to submit the forecast. In particular, we assume that experts recall their past forecasts and also observe the realizations and forecasts made by the other expert. Hence, the strategy of an expert is a function f, which maps finite partial histories to a probability distribution over the set of outcomes. Note that each forecast provided by one expert may depend, inter alia, on those provided by the other expert in previous stages. Let F denote the set of all forecasting strategies, and observe that a pair of forecasting strategies uniquely induce a pair of probability measures over the set of all realizations, whereas each single forecasting strategy does not necessarily induce a single measure due to the dependency between the two forecasters. So what is the abstract mechanism the tester uses in order to appraise the expert's abilities? So let F and G be two experts. One expert stands to the left, L, of the tester, and one to the right, R. The notation and order per Fg implies that F is on the left and G is on the right. At each stage, a tester must make up his mind by announcing his level of confidence, propensity, that the first forecaster, the one using F, is better than the second one. We calibrate these propensities so they add up to 1. Hence, we do not allow the tester to be indecisive. The tester is required to announce which expert he prefers at each stage, even if when F equals G. Albeit, he might swing back and forth between the two experts. Equivalently, the tester provides a recommendation for a coin flip over the forecasters to decide which of the two experts' advice should be taken. So at each stage, the tester is handed with 3 finite sequences: the realized outcomes and 2 finite sequences of 1-step ahead predictions which have been submitted by the 2 experts along the realization. Hence, the tester may condition his decision on any finite history of realizations and an order pair of forecasts. Formally, we say that a cardinal comparison test, T, is defined to be a sequence of measurable functions, each inputs a realization, two sequences of one step ahead forecasts corresponding to the two experts, and outputs a probabilistic rank, propensity over the two experts. Consequently, the tester ends up with a sequence of decisions. It should be noted that, by definition, the output of a cardinal comparison test solely depends on forecasts made along the realized playpath, and ignore what we call counterfactual forecasts. For example, relying on predetermined predictions about some tail event, which may or may not occur. In addition, it should be noted that the induced measure f is never revealed to the tester. The tester can only infer the marginals of f out of the corresponding forecasting strategies f and g along the realization. Some natural properties must be assigned to a cardinal comparison test. These are called axioms. Before we state the first axiom, we know that a realization omega, together with a pair of forecasting strategies f and g, induce a unique playpath, which is denoted by the triplet omega f g. The first axiom is anonymous. Recall that an ordered pair of forecasting strategies f and g implies that expert f stands to the left of the tester and expert g stands to the right. Hence, symmetry states that the tester's verdicts must remain the same whenever he just names the expert differently. Or equivalently, when experts just swap their places. Formally, we say that a cardinal comparison test is anonymous if for all realization omega, for all forecasters fg, and at each period t of omega fg equals y minus t of omega gf at each period t. Namely, the test propensity at each period must not depend on the expert's identity. Before we turn to construct a test which complies with a set of axioms, we introduce the following notation. Let LT epsilon be the set of realizations for which the limit of t exists, and from some time on it assigns a propensity larger than epsilon to f. Similarly, we denote by RT epsilon to be the set of realizations for which the limit of t exists, and from some time on it assigns a propensity less than epsilon to f. We will typically focus on the sets LT epsilon with epsilon larger than half, in which case f is preferred, and on the set RT epsilon for epsilon larger than half, in which case g is preferred. Hereinafter, we will typically use the pair fg, denoting the pair of measures induced uniquely by a pair of forecasting strategies. So let us introduce a set of axioms we deem desirable for any cardinal comparison test. Our next axiom is error-free, which plainly asserts that any set that is contained in R, the set of realizations in which expert G is preferred, must not assign a high probability according to F in comparison with the probability assigned by G. In particular, the ratio of these probabilities must be bounded by epsilon over 1 minus epsilon. Formally, we say that T is error-free if for all pairs of forecasting strategies, for all epsilon which is less equals than half, and for all measurable set A, relation 1 holds. Namely, each forecaster must believe that the test cannot significantly point out the other X forecaster as correct. From her perspective, she is either preferred or the test is indecisive. In particular, as epsilon approaches 0, the set RT epsilon captures the passes where expert G is clearly deemed better than F. The next axiom is reasonableness. We said that a cardinal comparison test T is reasonable if for any pair of forecasting strategies FG and for all measurable set A, if A is possible according to the right expert, G, and is relatively less possible according to the left expert, F, then there must be some sub-event, which is A intersection R, pointing to the right expert, G, as the better one, with some positive probability. Similarly, we defined it for F. We next introduce a test which complies with the aforementioned set of axioms. Namely, it is anonymous, error-free, and reasonable. Consider the following cardinal comparison test. We call it the finite derivative test. Hence, the ratio between D at time t plus 1, the rank associated with the forecast F, and 1 minus D, the rank associated with the forecast G, equals the likelihood ratio between the two forecasters. In other words, the tester uses a coin which probabilities are proportional to the ex ante probabilities of the event that occurred. It should be noted that low likelihood ratio score at the realization omega implies that expert F's predictions along the realization omega are turned out to be more likely than those predicted by expert G. Clearly, D is anonymous. The next theorem asserts that this test is anonymous, error-free, and reasonable. Indeed, theorem, D is anonymous, non-counterfactual, reasonable, and error-free test. For another property, we claim that D perfectly distinguishes between far measures. For example, D is settled on the better forecasters whenever the induced measures are orthogonal. Are there any other tests which are anonymous, reasonable, and error-free? Know that the test which yields half on day 1 and meets the test D from day 2 onwards is also anonymous, reasonable, and error-free. This motivates us to identify equivalent tests. Formally, we say that two tests, T and T hat, are equivalent at a pair of forecasting strategy FG if and only if there is a zero probability according to each forecaster that the test will converge to different propensities. We say that two tests are equivalent if they are equivalent at any pair F. We further claim that the above relation is an equivalence relation over the class of all cardinal comparison tests. Hence, the set of cardinal comparison tests can be partitioned into equivalent classes. In this context, the term uniqueness is referred to a class of tests which are anonymous, reasonable, and error-free. The next uniqueness theorem asserts that although there may be other error-free and reasonable cardinal comparison tests, they are essentially equivalent to the derivative test. Formally, let T be an anonymous and reasonable test. If T is not equivalent to D, then T is not error-free. Moreover, errors occur at all pairs F, where T is not equivalent to the derivative test D at F. It should be noted that error-free and reasonableness are not related notions. Indeed, as the following examples illustrate. Obviously, the test which constantly yields half is error-free. However, it is not reasonable. For example, whenever two orthogonal measures are inspected. To see why reasonableness does not imply error-freeness, consider the following example. Hence, T yields different outputs than D at only two places, which are induced by two measures which are absolutely continuous with respect to each other. The Dirac measure on 1, induced by F, and the measure which assigns half to the first outcome to be 1, and from day 2 onwards meets F. In which case, whenever the true process is the Dirac measure on 1, T yields an error term. Furthermore, since T is reasonable, it turns out that T is reasonable as well. Obviously, the anonymous of D implies the anonymous of T. It turns out that in order to determine whether a cardinal comparison test is almost certain about a forecaster, requires the two forecasters to provide significantly different forecasts. Formally, we say that a pair of forecasting strategies, FG, is epsilon close along the realization omega at period t if their corresponding one-step ahead predictions are epsilon close. We next present the main result regarding the uniform rate at which the derivative test D converges. Formally, the theorem states that for all epsilon, there exists a constant which solely depends on epsilon, such that for all pairs of forecasting strategy, Fg, and for all sufficiently large time n, which is independent of epsilon, there is a set of which the probability according to F is at least 1 minus epsilon, such that for any realization omega in that set, there are only two events which should be considered. Either F is epsilon close along the realization omega in all but k periods by time n, or the derivative test D is almost settled on the informed expert from time n onwards. It should be noted that the constant k is universal, as it is independent of the underlying process. In particular, observe that condition 2 implies that D is uniformly bounded below by 1 minus a small term which is solely depends on epsilon. Consequently, the theorem asserts that the only reason that the derivative test D is not almost settled on the informed expert at any arbitrarily finite time n is because the uninformed experts have made excellent predictions along the realization by time n. So most of the literature focuses on a single expert testing. The related question is the need to decide whether a single expert is a true expert or a charlatan. A seminal paper is due to DeWitt, who proposes the calibration test as a scheme to evaluate the validity of weather forecasters. DeWitt asserts that the calibration test must not fail a true expert. Foster and Vora shows that a charlatan who has no knowledge of the true process can produce random forecasts which are always calibrated. Sandroni generalizes the last result to an arbitrary finite test, stating that there exists no finite error-free test that is immune to such random charlatans. A natural question regarding multiple expert testing related to which expert might be preferred by a comparison test. In fact, we are only familiar with a very few such tests. In particular, Elnager introduced the following alternative cardinal comparison test. Hence, the test L differs from D whenever the likelihood ratio is high or low, but is finite. In which case, D does not decisively settle on any expert, but yields a propensity which depends on the proportional ratio, whereas the likelihood ratio test L does. In terms of the context introduced here, and unlike D, it turns out that L is anonymous and reasonable, but is not error-free. A different existing test, which was introduced by Feinberg and Stewart, is the cross-calibration test. This test checks the empirical frequency of observed outcomes conditionals on each profile of forecast. However, this test does not naturally induce a cardinal comparison test. Rather than ranks the experts, this test outputs a binary verdict, pass or fail, for each of the two experts separately, and hence rules out the anonymity. Moreover, it can be shown that any cardinal comparison test, which naturally ranks an expert according to its empirical frequency, would fail to be reasonable. The research proposes a normative approach to the challenge of comparing between two forecasters who repeatedly provide probabilistic forecasts. The paper postulates three basic axioms: anonymity, error-freeness, and reasonableness, and provides a cardinal comparison test, the finite derivative test, that complies with this set of axioms. Furthermore, it shows that this test is essentially unique. Finally, the test is proven to converge uniformly fast, and hence is meaningful in finite time. Thank you very much for listening.